Hi friends, are you waiting for the results of the Physics Olympiad selection? Hopefully you get the best results. Let's learn, so that on the next occasion we can go through the Physics Olympiad selection even better. We have a question that I think is quite interesting. You can pause this video for a while, to read this question in detail. This is a floor surface. A horizontal surface on the left side, and an inclined surface on the right side. Apparently this surface is quite rough, so much so that a yo-yo can roll through the track. The yo-yo rolls from a flat surface to an inclined surface. What's interesting about this question? The criteria is that the yo-yo can roll through both tracks without jumping. At low speeds, the yo-yo can most likely do it. However, at high speeds, this yo-yo will jump towards the inclined surface. This is an undesirable condition. There must be a maximum speed, where the yo-yo changes from rolling to jumping. We will calculate the maximum speed. Let's discuss. So that we know what we are talking about, we will identify some quantities. Let's say the mass of the yo-yo is m, its radius is r. For the inclined surface, let's say there is an angle theta to the horizontal surface. Then what about the level of surface roughness? Here the rough surface only causes the yo-yo to roll. After the yo-yo rolls, the frictional force does not absorb any energy at all. So we don't need to write the coefficient of friction. Observe the movement of the yo-yo for a few moments. What can you conclude from the movement? That's right. Actually, the yo-yo does 3 stages of motion. The first movement, the yo-yo rolls through a flat surface until it reaches the end point. In this movement, the axis is the center of mass of the yo-yo. The second movement, the yo-yo rotates. In this movement, the axis is the end point of the trajectory. The third movement, the yo-yo rolls through an inclined surface. In this movement, the center of mass of the yo-yo becomes the axis again for the second time. Knowing this separation of motion is very important for further analysis. In the first part, at every point of the flat trajectory, the yo-yo will have the same parameters. Assuming that the frictional force does not take any energy from it. So overall, all the movements in the first part can be represented by the movement of the yo-yo at the end point. The yo-yo at the end point already depicts the initial condition. By the same analogy, the yo-yo at this point already depicts the final condition. We will analyze the movement of the yo-yo from the initial condition to the final condition. Up to this point, the concept is still easy to understand. In the initial condition, what are the parameters? The yo-yo has a linear velocity of v0 to the right. It seems that this maximum value of v0 is what we want to calculate. The height of the center of mass is measured from the horizontal surface. From the initial condition to the final condition, the yo-yo rotates about the end point of the trajectory. Just before reaching the final condition, the yo-yo has reached an angular velocity of omega 1. At this time, we do not know the value of omega 1. The center of mass of the yo-yo is now changing. We can draw a straight line from the end point to the center of mass of the yo-yo. The length of this line is none other than the radius of the yo-yo. The radius of the yo-yo is always perpendicular to the contact surface. It is certain that this angle is theta. From here, the height of the center of mass is now our cosine theta. We already know the parameters for the initial and final conditions. It is a common belief that if we know some parameters at different points, then we can test the law of conservation of mechanical energy at both points. Let's just write, the mechanical energy at the initial condition is the same as the mechanical energy at the final condition. Since there is no energy dissipation, the mechanical energy consists only of potential energy and kinetic energy. The potential energy is measured from a reference. We will use a flat surface as the reference line. The potential energy of the yo-yo is mgr. For the kinetic energy, between the initial and final conditions, the yo-yo is only rotating about the end point. The end point remains there, it does not change with time. So, the yo-yo only has rotational kinetic energy, half I omega 0 squared. The yo-yo is rolling, it is not slipping. Omega 0 is V0 over R. For the final condition, its potential energy is mgr cosine theta. The rotational kinetic energy is half I omega 1 squared. The tricky part is to determine the moment of inertia of the yo-yo rotating about this axis. We need to know about the parallel axis theorem. From the standard table, we know that the moment of inertia of a solid cylinder rotating about an axis of symmetry is half mr squared. In our case, the axis is here. How do we get the moment of inertia for this axis? You can apply the parallel axis theorem. This theorem is currently discussed in detail in the member videos in the rotational dynamics course. In short, the magnitude of the moment of inertia on the axis parallel to the axis passing through the center of mass is I new axis equals I center of mass plus md squared, where d is the distance between the two parallel axes. The axis of the moment of inertia half mr squared is the axis passing through the center of mass. The distance between the two axes is r. So, the yo-yo spinning like this has a moment of inertia of 3 over 2 mr squared. We can substitute this value into our equation. To make it look simple, you can write this equation like this. In this equation there are two unknown quantities, omega 1 and V0. We need one more equation. Where do we get this equation from? The motion of the yo-yo in part 2 is actually a vertical circular motion. There is a centripetal force there. Therefore, we need to identify the force that is toward or away from the center of rotation. Of course, the force of gravity is acting on the yo-yo. However, the direction of this force is vertically downward. We need to dissolve this vector into its component vectors, mg sine theta and mg cosine theta. Between these two component vectors, the direction of the component vector mg cosine theta is toward the center of rotation. At the final state, the yo-yo is also touching the inclined surface. The normal force is also acting on the yo-yo. However, this time, the direction of the force is away from the center of rotation. Mathematically we can write, mg cosine theta minus n is equal to m omega 1 squared r. Because we are asking for maximum velocity. At the limiting velocity, the yo-yo will not touch the inclined surface. We can say that at maximum velocity, the normal force is 0. N is equal to 0. This is equation 2. Now we have two equations with two unknown quantities. Which of these two quantities do we want to calculate? V0. This is correct. So we need to eliminate omega 1. Okay, let's write equation 1 as omega 1 squared. Then, substitute that value into equation 2. Up to this point, we just need to hone our math skills. We can break down the factors on the right-hand side. Next, collect all the factors that do not contain V0. Write this equation as V0 squared. From here, V0 is equal to the square root of 1/3 of Rg, multiplied by 7 cosine theta minus 4. Is that enough? Not yet. The value inside the root may be negative. There is one more condition. In order for the value in the square root to always be positive, the value in the brackets must be more than 0. 7 cosine of theta minus 4 must be more than 0. The cosine of theta must be more than 4 over 7. Or theta must be more than the arcsine of the cosine of 4 over 7. This is the answer to this question. Hopefully this question can improve our ability to answer physics questions.